Tyson, and for my final GIST project, I decided to do a project on the moon. And the project I chose specifically is in analyzing potential optimal corridors or routes for the construction of a lunar South Pole oxygen pipeline. This is something that is in the works. It's working. There are many different agencies actually on this problem set right now. So I saw kind of a place where I could inject myself into this, and I did. And I'll go into that as we proceed. So contents, I'll start with the introduction, go over the South Pole lunar pipeline, the oxygen extraction process, and in situ manufacturing, which essentially means using materials available on the moon to do this project. Then I'll go over all the methods I use, the data, and then the analysis. And I bullet pointed here the 3 points I'm going to make is these 3 different feature layers are the layers that I use to ultimately create the final product of the analysis. And that's the optimal paths line, the most favorable terrain layer, and then a corridor distance analysis. And then we'll finish with results and conclusion. So starting with the introduction. So research, like I said, has been ongoing through the Artemis program through NASA for this pipeline. NASA found the problem which created the need for the pipeline exists based on drones. The drones were too expensive, they found, and would be too costly to either move the oxygen in small trucks or some trains. There was some different proposals that they came up with, and the best that they saw was the pipeline solution. And so after that, NASA actually awarded $176 million to 14 different research agencies in order to chase after this problem. And so there, like I said, this is all part of the Artemis program. So there are some kind of early stage planning with it. However, I in my research never saw anything or understand anything, and anyone I spoke to of any location that's been planned so far. They've come up. They're planning right now. The one agency is planning up to the NASA Space Lab is planning a 5-kilometer section. So they haven't gone longer than 5. My pipeline route is a lot longer, but they've only planning for 5 kilometers right now with no known location. Just knowing that there's concentrations of polar ice at the South Pole, and then there's that they know the lunar base will be somewhere in the equator. So those are the assumptions I based my study off of. Moving on. So the pipeline itself, the South Lunar Pipeline. So it'll be made from aluminum, which is in situ available on the surface. So aluminum is prevalent on the lunar surface. Most prevalent on the south, actually, is along with the ice, but it is prevalent across the lunar surface. It'll also be constructed and maintained using drones. That's the plan right now. There will have to be some human involvement with that. And it will be made using the same process, actually, as the oxygen extraction, which is the molten regolith electrolysis. And that what it does is it heats it up, and it will and you add hydrogen to it, and it extracts the material from the regolith itself. And regolith is a name given to basically essentially moon soil or moon rock. And this pipeline will be designed to pump either liquid or gas. So the idea is the oxygen will be liquefied at the source or liquefied at the destination. So it can be designed for both. For the oxygen extraction itself, there have been 20 different proposed methods to do this. And as I mentioned a minute ago, the most feasible method is called MRE, molten regolith electrolysis. And that process heats up the regolith, the ice-infused rock, to approximately 900 degrees centigrade, and hydrogen is infused in it to reduce it and separate it, essentially. Once they separate it, then they can separate it, liquefy it, or keep it as a gas, and then transport it. And then so the idea would be transporting to a lunar base or storage facility. And as you see here on the slide, I have a couple little images. So this is just a depiction of a possible oxygen facility. And then the image on the left is from the Colorado School of Mines. It's the different states in which ice exists in the moon within the regolith itself. And as a note, the middle column, bottom row, the ice matrix breccia you see there, that is the type of ice that's located in the ice concentrations in the South Pole that we're interested in. In situ manufacturing, meaning on-site available manufacturing for the pipeline itself. I found this kind of neat, design study image here showing an astronaut working in a site building the pipeline. But that's the idea of it, is using on-site material to essentially forge and make these pipes in segments. They'll be done in modular segments, so they can be manufactured more uniformly. They can be done with drones in a way that it'll be it'll be more cost effective that way as well. So everything will be very modular. That's how the plan. Everything will be modular, and of course, including the pipeline. It supports as well as the line itself. And it'll be mostly drone run, essentially. In the beginning, there might be some, obviously humans will be involved, but in the end, they want to have the long roll, and they want to have drones running mostly everything with it. Okay, so getting into the methods. I used 10 different geoprocessing tools for this. Source data was input into certain tools and output, and then certain tools needed the output of other tools as their inputs. And I'll show you some visual depictions so that makes more sense. And then feature layers were in the end refined using transparency and different mapping techniques to give a better visual representation in my final product. Here's my workflow diagram. I know it's a little bit busy, but if you look at the blue ovals, that's essentially my source data. The orange and yellow are my inputs and outputs, and the green ovals are my ultimate desired layers. That's the optimal routes layer, the favorable terrain units, and then the corridor distance raster. And I will go into this flow in detail, but essentially each process had a certain number of tools that required them to work in an adjacent order in order for me to get the desired results. Okay, going on to the study area used. The area used encompasses approximately 17% of the moon's surface. So it's a very, very large part of the moon I was studying. And the reason why this area was specifically chosen, well, it covers all possible routes between the concentrations of lunar ice on the South Pole as well as the equatorial lunar base points. And those points were decided based on orbital trajectories, easy return Earth trajectories, as well as past Apollo missions as well. So looking at those points, there were some assumptions made about where a lunar base would be more or less located. More or less straight north of the ice concentrations, and that's where I came up with this specific study area. Next, we had the lunar surface base map. I had a lunar surface DEM, or digital elevation model, which was used for geoprocessing on the slopes and everything for the routes and the optimal line tool. Geologic terrain units in polygons. So each of these polygons represents a different unit. So plains, crater, partial plains, medium crater, steep crater. There's different designations for terrain essentially. And what I was always searching for was plains, anything that was flat and easy to build on. And next was all lunar craters point data. So this is a point data set I got from USGS. It just shows all. If you zoom in, you'll see craters that are missed by the dots, but these are all the dots represent craters. Some dots will be the same size as a crater that's a lot larger than it. So it's not perfect, but it's good enough for at least getting an idea of how the density of craters. Next is the concentrations of near surface lunar ice. This is the South Pole view. I gave this view because it's a lot easier to see the ice actually from the South Pole of the moon. And you'll see this same feature set in different equatorial views as well. And that's the last data set we had. Moving on to the analysis. So this was the next several slides is for the analysis used for the optimal path, this line tool. This is the tool that produced the actual routes. This is the real kind of meat and potatoes of my analysis. So beginning, I used the DEM, input it to the clip raster, and output into the actual study area itself as a clip, as you can see here. Next, the all craters input was input into the buffer tool, and I buffed each crater with a 10-mile radius, meaning that each one of those dots had a 5-mile 5 mile on each side, or 10 mile on each side radius, creating that dot in size. And the reason why I needed this set was for obstacles. So when the geoprocessing analysis was being conducted, I didn't want the routes to go through any of these dots. So that was the purpose of this. Next, for the optimal path is line, I took the craters buff, the DEM clip, and then the lunar ice points, those points in the ice concentrations. Using the distance accumulation tool, it gave me two outputs, a degree distance raster and a distance raster. The degree distance raster used the ice points as sources. You can see where all of these colors coalesce is where each ice point is, and each one designated a color and a degree for each direction. So I know this is a little hard to see, but you see north, south, source, and they'll have different points given for different directions. This gave a distance from the points outward in a 360 direction. So you'll see green, less distance, over to amber, into red. And those are the two inputs that the ultimate tool needed, the optimal path is line tool. So the optimal routes were created by putting the degree distance raster, the distance raster, and the lunar base points into the optimal path as line tool. And then the output produced my routes. And on this map, I also added the near surface ice points, these little blue dots, as well as these red 3 perspective lunar bases that I had to mention. So that produced my actual routes, optimal routes. Next, for the most favorable terrain, I wanted to get the terrain units that intersected the routes, and then I wanted to segregate the best of those. And so how I did that is I inputted geo units and the optimal routes into the select by layer attribute tool, which created a terrain along routes layer. This layer here is the same as this layer here, the blue you see. And then that layer was inputted into the select by layer location, which the output gave me most favorable terrain type, which you see on the map here is green. For the corridor distance, this is the equatorial view. I'll give 2 views of this. This places a cost based on the distance for each route. So looking at this map, you can see the blue here shows that the first route, I call it route A, the route first to the left, as the best route as far as corridor distance. In order to get that, I used the optimal routes layer into the cost path, which created a cost path raster, which its input was for the corridor analysis tool, which then the output leading to the actual corridor distance raster. And here is a southern pole view of the same raster set. As you can see, the blue kind of shows the more feasible corridor as far as distance when it was computing. So the results and conclusions. So the resulting map you see are the key layers overlaid over each other with a route designated for each one. The routes show the feasibility of each layer. You can see underneath the blue with the corridor, and then the terrain units over that, with the green terrain is the most feasible, the most desirable. That terrain is like flat, plain sand, no obstructions, as well as you can see the crater's buff. And at this extent, it's hard to see, but the analysis when it was calculating the routes, it avoided every crater as an obstacle. So data suggests that Route A is the most suitable, based on a lot of that's based on, of course, distance. And I want to show this route, this next map here. You can see now, looking at it from the south, you can see the more curvature of the global curvature of the moon on the Route A. So kind of shows a little bit better the actual, the route will have to be built on much more of a curve than you could see earlier. The distances total for the routes, Route A came out at 1,273 miles, at B at 1,375, Route C at 1,448 miles. So Route A a lot shorter. There's not a large difference between the different routes. These endpoints obviously can be adjusted, shifted. This is something that we would use for kind of initial planning to see where things would go from there. But at least this gives a good baseline for what distances that we would be faced with building such a thing, and kind of the logistics involved with that. And then as another note, Route E does pass through 160 miles of favorable terrain. Route C passes through the most favorable terrain. However, Route C is the longest. So there are some different assumptions and risks you'd have to mitigate or accept going forward with a project like this. And any questions? And this image here is, of course, what the pipeline will make the moon look like ultimately. Thank you.